Yeah, so I probably will have it ready. I mean, I'm sure like I'll send it to tomorrow at some point. So I'm like, yeah, I'm writing like a study guide of the basic formulas you need to know for the exam. Um, and also like if you're checking the, I mean, it also includes like a summary of like the format of the exam. And I'm also mentioning which sections from the book to check in case you're looking at the book, and which problems to look at from this PDF problems guide. And yeah, like the exam will be very similar to those problems that I'm recommending. So basically, if you don't do like those problems on the PDF, you'll be good for the exam. I'll also give you like probably share like one or two practice exams, and I'll give you the solutions to those. So that should be more than enough. I mean, like we haven't covered that much material yet, so I just wanted to have three exams, three midterms, for lack of a better word, during the course before the final, so that none of the exams would be worth that many points. So that's the only reason why we're doing that exam like next Monday. Um, but yeah, there are not that many formulas, and if you do like the problems, like if you have understood like the problems we have been working on, plus those that I'm recommending, then you should be fine. Um, but yeah, like I won't like yeah, like, but yeah, I'll give, but you should have enough. It will be very predictable. Like the probability that the problems will be on the exam will be similar to the ones on the study guides, and all of these will be very high. So
Okay, cool. And we're allowed a calculator on the exam also?
yeah, you can use a calculator. Yeah, that's not a problem.
But
The
no
only
note
the
sheet.
Yeah, the only thing is that no cheats. That at the same time, like there are not that many formulas. Like really, at this point, we don't really have too many formulas to memorize. I would say only like really like the n chooses k. I cannot believe of like the others are kind of like straightforward. But yeah, like no cheats. But yeah, calculators are fine. I don't mind that. Um,
Okay.
now, it's not that you have to use a calculator. So, for example, just to like, if you can still see this, like, if you have it, like, if one of the answers you get like is 6 factorial divided by 2 factorial, 3 factorial, you can leave the answer like as that, and in a sense, that's okay. I mean, that's totally fine with me. It's just that sometimes, to get like a sense of the actual numbers, you may just want to plug it into a calculator uh, to see what you end up getting. But I mean, I would say if you just want to like leave the answers in terms of factorials or things like that, then that's totally fine. Don't leave the like for the combinatoric symbol, like don't leave it like just like this. Well, I guess it is fine also. I mean, this is kind of clear what it is, so you can leave it like this, or if you prefer, you can rewrite it as 5 factorial, 3 factorial, 2 factorial. I mean, either will be fine. So I'm not going
Okay.
to ask. Not going to ask you to kind of like compute the numbers, but I think it can be useful just to get like a sense of what numbers you're getting to plugging them in a calculator. So uh, yeah, but
Okay,
yeah,
cool. Thank you.
yeah, sure, no problem. But yeah, I do hope to. I mean, I'm almost done writing this, so I'm sure, like I'll send you this PDF with this information for the exam at some point tomorrow, and once I send that to you, I'll also send you like to practice exams, and then I'll send you sometime during the week on Friday or Saturday, like the solutions to the practice exams. Um, like if like today's roughly like the last day I was planning on covering material for the exam. In a sense, like I actually kind of went through almost all of the formulas that I wanted to go for the exam Monday. So like I was just going to say a very few things and then do like a couple of examples. Um, okay, so what is today's lecture 5, I think. So let's see. So the last formula that we were discussing last time, you can kind of see it a little bit before on the iPad, on the notes, but let me just repeat it. So again, like in this visual representation, like you can think of the propositions or the statements S1 and S2 as representing some fraction of everything that can happen. So what the rule for the last rule for probabilities that I gave you last time says, it's kind of a generalization of the case when S1 and S2 were mutually exclusive. What this is saying is that probability of the union, like the union means the same as OR. It's like the probability of S1 plus the probability of S2 minus the probability of the intersection. Okay. So this is I mean, this is one of the important formulas involving probabilities. I'll give you like a generalization of this in a couple of minutes. But I mean, it does it is very useful. So for example, here's another way to use it that has like interesting application. So one way to think about this, let me write it. Let me flip the size of the equality. So you like this, what I'm saying is that the probability of S1 plus the probability of S2 minus the probability of the intersection is the probability of the union, right? That's just the same. But what's the probability of the union or the OR? Well, that's a probability of a statement or a proposition. So any probability, remember, is always between 0 and 1. So you can say that all of this, right, is less or equal to 1, which is kind of silly, but I mean, it is true. So you end up with this inequality. That this is all of this is less or equal to 1. And so if you just rearrange it, the inequality, so that this one goes to the right hand side, because right now it's with a minus, so it's convenient to move it to the other side so that it's plus. You end up with this inequality, which is called Bonferroni's inequality. Which says that the probability of S1 plus the probability of S2 minus 1 is less or equal to the probability of the intersection or the end. So this inequality gives you like a lower bound for the probability of two things happening at once, or two things being true at once. So this is tells you that this probability has to be at least as big as this quantity. Okay, so I'm about to give an example, but are there any questions about this? Is that making sense? So let's do an example. So where do I have it? Oh yeah. So and again, it's kind of fun that it is so S1 could be I will order pizza for dinner. And S2 would be, I will order ice cream for dinner. So just to give concrete numbers to this, let's say like, that the probability of S1 is 0.7, assume the probability of S1 is 0.7, so like a 70%. And maybe you're more certain that you'll order pizza or ice cream. So let's make this slightly bigger probability. So it's 0.8%, right? So a question could be, what's the probability that you will order pizza and ice cream? So here's like the question. Or what's the minimum? I mean, we won't get the number per se, or how should I say it? Give a number. And again, this is just like a simple application of like this Bonferroni inequality. So I mean, just plug it in. It's more like recognizing that you could use this inequality. So if you look at the inequality, well, the probability of S1 plus the probability of S2 minus 1 is smaller or equal to the probability of S1 and S2. Okay, so this is 0.7 plus 0.8 minus 1 is at least is smaller or equal to the probability of the intersection or the AND. Okay, so that's what? That gives you 0.5 minus 1, so that gives you 0.5. So that means that there's at least like a 50% chance that you order pizza and ice cream. Is that making sense? Again, like for these examples where I'm putting just food items, that may not be so interesting, but again, like you could think about this like having medical applications or applications to biology, population genetics, other things where you want like, you may ask for the probability that certain individuals have two different traits or like have two different diseases, things like that. So, I mean, there are many more interesting ways to play around with this, like inequalities and things like that. I'm just showing you like a very simple thing to, put like kind of like give you some idea, but it is like, you could imagine like just making the example like juicier for lack of a better word, like, Is that making sense? Are there any questions about this example? In fact, I mean, on Friday, like as I said, today will be the last topic, the last day we cover things for the exam. But on Friday, we'll start talking about conditional probability, which is really where like the stuff really gets interesting because there are many non-intuitive things about conditional probabilities. And we will get to one of the most important formulas in probability theory, which is called the Bayes formula, and has many surprising applications. So that's like a fun part of the course to talk about conditional probability. Okay, now let's talk about another formula. So, okay, here's a generalization of this formula for the probability. So we just saw like the formula for the probability. We just saw a formula for the probability that one thing will happen or another thing will happen. There's a generalization like to 3 or more events. So let's do the case of 3 because like that will give you like an idea of what happens in general. Let me see if I can do this. So let's say that I give you 3 propositions, or these are also called events. So the event could be like, or the statement could be the dice falls on a 6 or falls on an even number. Like, you know, it's just like something that potentially could happen, something that has a chance of occurring. So I give you 3 of them, and I ask you for the probability of at least one of them occurring. So I want to find. So what, in terms of this diagram, means it would be, again, like what I was mentioning last time, is that you can think of this probability as kind of giving you like as relatives. Like if you thought about this like as a form of area, because like it just looks being drawn on the plane. This is kind of giving you like the probability kind of gives you like a size or like the relative fraction of how much this occupies with respect to all like the larger space. So like there's also a convenient way pictorially to think of this probability as some sort of like relative on some sort of ratios in terms of like size. So basically, like almost like ignore like the problem about probability. Imagine like I gave you these 3 disks, right? I gave you these 3 disks and I asked you for the area, like the region that I'm coloring of right now, in terms of the individual areas of the disks, right? Well, so like the first thing you could say is like maybe, well, first you could just consider adding the areas of the disks, right? But what happens when you if you add up these areas? Well, or these fractions, the thing is like there's some overlap regions, right? So they are, if you just add these quantities, like they're just being counted more than once. So let's let me color in green the stuff that is only being counted once. So this is being counted once, right? This is also being counted only once. And this is being counted only once. So I'll put a 1 just to represent how many times it's being counted. But now there are like these pieces that are being counted more than once, right? So this piece, right, is being, these pieces are each of them being counted twice when you added up all these areas, right? And how about the last one? The last piece, how many times is it being counted? It's being counted 3 times, right? Is that making sense? So now I have to correct for the fact of the overcounting, right? So for example, how can you correct for this overcounting? Well, you can you can start subtracting like you could subtract at least, oops, if you subtract this piece and this piece and this piece, right? What is this first piece? This first piece would be in S1 and S2, so it's like an intersection. This second piece would be in S1 and S3. And this third piece, oops, would be in S2 and S3, right? But so if I remove one of these pieces once, right, I drop the count from 2 to 1, from 2 to 1, from 2 to 1, right? But now the question is, is that okay? Did I create did I cause an extra problem now? Is there like an extra issue? Does like the formula need something else to to fix it? Yeah, right. Because the thing is like the blue part, the blue region belongs to each of the pink regions as well. So when you subtracted it 3 times, you went from 3 to 0. So it's no longer being counted. So you have to at least add it once so that count also goes to 1. So this gives you have to recover it by intersecting. The blue thing belongs to all of them. So you just add up the probability of S1 intersect S2 intersect S3. Is that making sense? So that's the probability for the union of 3 events would be computed. Is that making sense?
Just to clarify on my end, like in the context of this problem, could you think of the probability of the union of the 3 events just being like the area here?
Yeah, it is like it does right. Strictly speaking, it's always like a ratio of this, like if you thought it in terms of the picture, it would be like the ratio of these areas relative to the larger area.
Yeah,
because
gotcha.
that's what it makes it to be like a number between 0 and 1. But like since the larger area is kind of fixed throughout the problem, it is kind of like a common denominator. So you can just add up the numerators without issues. And that's when you can really just think about it in terms of the area. Or you just do like the usual convention that you just think that you're using units or whatever, like where the larger area is literally just 1, 1 in whatever units of area you want to use. And so everything has been rescaled so that really these are just always like areas. Is that making sense?
Yeah, that makes sense. Thank you.
Sure. I mean, I'm just saying like, again, it will be, once we get to the continuous probability case, if this is more correct, this is more true in the sense that we would think more of these probabilities as giving you some sort of like sense of proportions of like area in terms of areas or volumes or lengths. For now, it's just kind of more like a pictorial representation, which is useful to become convinced of these formulas. I mean, there are other ways to get to this formula. One is called the induction method and things like that. But I think it's, I know it's kind of like I like these proofs by picture arguments. They're kind of fun. But yeah, you could prove this by induction. If you read the book, that's what they do. Or like they kind of like begin for the formula for 2 and then get the formula for 3. But it's nice to kind of like have a picture of the situation for what this is. Is that making sense? So let me, so I wouldn't expect you to memorize this formula. So if you need it on the exam, I will just give it to you. There's also like a generalization for S1, union S2, union S3, union S4, like, you know, it continues, but like more than 2, I would just give you the formula. So like, this is like, you know, I think it's kind of like, okay, I do expect you to kind of know this one. But like for 3 or more, I would just give you what the formula for the union is, because like it can be a little bit difficult to memorize. So of course, if you know the picture, it's kind of maybe relatively reasonable to recreate it, but you don't have to worry about memorizing this one. So I'll just put it here as an aside. Okay, let's do an example with this formula, which is kind of interesting. I like this problem. And you'll see that, and this is more like the last formula that I wanted to include for the exam, just in case. But this is like the PDF. Let me see if I can find the number. I think it's problem 9 on the PDF. Let me check if that's the correct number. Yeah, this is problem 9 on the PDF. So I'll do like a baby, you know, for these problems, I always prefer to start with the baby version of the problem and then like the grown-up version where we just do it like in more generality. So I will reword the problem a little bit, but let's say you're old-fashioned, so you have 3 friends and you are writing a letter to each of your friends. In the problem, how I wrote it is in terms of a secretary, but let's just do it this way. You have 3 friends and you are writing a letter to each of them. So you're writing 3 letters in total, right? But okay, and when you send a letter, right, you have to put it you have an envelope where you put the address of your friend on the envelope, but you were not paying attention, and so you just like put the letters at random in the corresponding envelopes. You were not paying attention. So you just put one letter on each envelope at random. So is the problem making sense so far? So, you know, you had you have some envelopes, right? You're writing here like the address of your friend. Each envelope has an address. You have 3 letters, but you're distracted, so you just place like the letters, like one letter on each envelope, but randomly without paying attention if you're matching the like who this who you're like writing the letter to with the corresponding name on the envelope, right? So the problem is, what is the probability? Here's a question. What is the probability that at least one letter is in the correct envelope? Is the problem making sense? So what is the probability that at least one of your friends will get the letter that was meant for that particular person, and not the letter that was meant for one of the others? Okay. So is that okay? Any questions about the statement itself before we move on to solving it? Okay, so okay, the first thing you could do to solve this problem is the brute force approach, which is fine. So it's not, I don't mean it as an insult. It's actually good to do it like sometimes as brute force. So brute force approach would be just to list all the list all the things that could happen and just count in all these scenarios, in how many scenarios at least one friend got the right one, and how many scenarios none of your friends got the correct letter. So try to do that. Like that actually takes like 3 minutes if you list them correctly. So let me bring just some water, and in 3 minutes we'll discuss it. And that once we have the correct probabilities, we will think about it in a more elegant way, which we can then generalize to the case that you have not 3 friends, but like n friends, like 10 friends, 100 friends, and 1,000 friends, and you'll see what happens in that case. So, but think about it in brute force approach to see how many they are. So let's discuss in 3 minutes, but if you know the answer, like don't say it right now. So was anyone able to make the brute force list of how many what do you think the probability should be then?
I did the brute force where I found 2/3.
Okay, good. Let's check it. I believe you're correct, but it's always, I also did it brute force like to make sure that I had the list somewhere in here. So here's like the brute force approach, which again, brute force is good because it's nice to go through everything in full detail. But it's not, and then, but then we'll do the elegant solution. So brute force is like, okay, here's like a possibility. So what do I mean by this? Like, I mean that this is like in a scenario where your first friend got letter 1, your second friend got letter 2, and your third friend got letter 3. Okay, but here's an scenario, like this is in a scenario where like your first friend got letter 1, your second friend got letter 3, and your third friend got letter 2. So for example, in the first possibility, it is kind of the best scenario, right? Every friend got the letter that was meant to this person. But in the second list that I'm making, only the first friend got the right letter, and then you kind of switch the letters for the other 2 friends. Is that making sense? How I'm listing them? Is that okay? So like, and so again, just to repeat like what this means. So in this listing, that means that your first friend got letter 1. Sorry, your first friend got letter 2, your second friend got letter 3, and your third friend got letter 1, right? So this is actually like the worst possible case, right? No friend got the letter that was meant for them, right? Is that making sense? So now what I'm asking you to is to check in which of these scenarios, like actually at least one of them got the right one. So here are the scenarios. Like in this case, at least this one got the right one. I mean, the other two also got the right one, but I'm just like this indicating that at least there was one positive solution. This one got the right one in this case. In this one, like for example, this one got the right one. Like here, there seems to be that no one got the right letter. It looks like no one got the right letter here either. And in this one, like at least the second friend got the correct letter, right? So I'm just marking that at least one possible outcome. Like here, there were more than one, and that's fine, but I'm just asking for at least one letter being correct. So I don't care that there are more than one. Is that making sense? So yes, correct, exactly. So yeah, by counting, it's like four possible outcomes, and there's like the totality of 6 listings. So it's 4/6, right? So it's 2/3. So it seems like we're getting to the correct answer. So 4 positive outcomes, 6 possibilities in total, since 6 possibilities in total. So the probability should be 4/6, which is 2/3. Is that okay? And again, what you have to imagine is that if I had told you you have 10 friends and you're writing 10 letters to your friends, you don't want to do this, right? It is not recommended that you do this because now you have to put 10 slots, right? And how many would that involve? 10 factorial, right? 10 factorial is a big number. So you like 6 is 3 factorial. So that's why it wasn't too bad to go through this list. Okay. But so we have to come up with a better strategy that will allow us to generalize it to the general case. Okay. So what's the better strategy? The better strategy is actually to use like a formula like this, which seems a little bit of an overkill in this situation because you can just do the count, but you just realize that in the general case where you have 10 or 100 friends, it is like a better solution. Okay. So here's like the more elegant solution, elegant approach. So I'm going to use a formula for the probability of S1 union S2 union S3. So the first thing is that in this case, in order to use the formula, you kind of have to call something S1, S2, S3, right? You have to give names to those like the things that appear there. So I'm going to go call S1 the situation where the first friend gets the correct letter. So S1 is going to be now friend 1 gets the correct letter. S2 is going to be friend 2, or my second friend, right? Gets correct letter. And S3 is going to be the probability, like the event or the proposition that the third friend 3 gets the correct letter. Okay, So P probability of S1 union S2 union S3, that means the probability that the first friend gets the correct letter, or the second friend gets the correct letter, or the third friend gets the correct letter. But again, this or, the way we use the or here is what is called the inclusive or. So we are allowing for more than one possibility to occur. So that's why this actually does give you the probability that at least one friend gets the correct letter. Is that making sense? So we're after that probability. And if you look at that probability, that probability for by that formula would be what? Probability of S1 plus the probability of S2 plus the probability of S3 minus the probability of S1 intersection S2 minus the probability of S1 intersection S3 minus the probability of S1 intersection, sorry, S2 intersection S3 plus the probability of S1 intersection S2 intersection S3. Okay, that's like what the big formula says, which again is an overkill, but it's like what will allow us to generalize for like the case of n friends, which which is what we're after. Okay. So let's start with the first line. What do you think, for example, is a probability of S1? So that's a probability that the first friend got the correct letter. What's that probability? What would you say is that equal to?
1/3, right?
It would be 1/3. Okay. Okay. There are a couple of ways to see that. Good. First of all, like you should convince yourself that the problem is completely random. So there's no like asymmetry between the friends, right? Like the problem doesn't suggest that there's like a preference in, like you have to imagine like this person when they were assigning the letters was completely looking the other way. So there was no preference being made to a friend. So that tells you, first of all, that the probability of S1 should be the same as the probability of S2, which is the same as the probability of S3. So they're all equally likely because nothing in the problem suggests that there was like a preference, like in the moment where this random assignment was given. Like actually, that's kind of almost what the word random means, like hidden in the statement. So it should be 1/3. Good. So there are a couple of ways to think about it. As so, if you had, let's say you didn't have 3 friends, you had n friends, right? So if it were like n friends, it would be 1/n, right? So if you had like 5 friends, it would be a fifth. Like hopefully, you'll see why this is plausible. So what I'm saying is that it's really 1/n if n is the number of friends. Here, n is going to be the number of friends. It's just that we're taking n to be 3 in this example. And then a way to see this is that this is really like n minus 1 factorial over n factorial. That's like the maybe most elegant way to see that, because like kind of like you know, you have to place in this cases, like at least one letter is going to the correct spot. So you only have n minus 1 spots to play with, right? So that's why you get like n minus 1 factorial, and then there are like n factorial totalities possibilities. Is that making sense? So like this is like again, where I'm trying to aim for the generalization of this formula. So this is the correct generalization for this formula. Okay. For the case of n friends. So this, like if you had 10 friends, the probability of one friend of like the nth friend receiving like the correct letter would be 1/10 and things like that. Is that making sense? Okay, now let's go. Let's go to the probability of S1 intersection S2. That means the probability the first friend got the correct letter and the second friend got the correct letter, right? So what is the probability?
I got a 1/6 for that.
Okay, let's see. Yes, so let's check. So so what I'm saying, okay, like just to explain this again, like where's the n-1 factorial coming from? I'm just trying to write like the formula here in the case you had n friends, not just 3, right? So for example, let's just do it for S1. What does it mean? What would have been like the probability for, like, just let me explain this here. What would be the probability for S1? That means that in the first slot, the first friend got the correct letter, right? So there should be a 1 here, but then there are like n-1 spots available, right? And for this event, I don't care where they are going. So in how many ways can you place n-1 letters here? Like you have n-1 factorial ways to rearrange them so the probability would be n-1 factorial divided by the total number of outcomes, which is n factorial. Is that making sense? So yeah, in this case, first, it's kind of similar. The probability of S1 intersection S2 will be the same as the probability of S1 intersection S3, which will be the same as the probability of S2 intersection S3 because everything is completely symmetric. There's no difference between the friends. And this will be 1/6. Oh, let me write it here. But I want us to think about it more, like it is easier in this case to think about it along these lines. So what would you put here? Like what would be the analog for n? It's actually kind of easier to see the formula first for n, for general n. So what would be the analog for n of this formula in the case of 2? Like, yeah, it would be exactly, it would be n-2 factorial. So I have n factorial options, right? But here, like this means that 2 friends got the correct letter. So there are 2 boxes that are reserved because those have the right numbers. So I have only n-2 remaining options to play with. Is that making sense? So this is n-2 factorial over n factorial. Is that okay? So and the last one is a probability for S1, S2, S3. And it's kind of almost easier to give the value first for n fact, like for the general case. What's the formula for the general case? What do you think it is? It's with n-3 factorial, right? It's just that in this case, because we're only dealing with 3 friends, it just gives you 1/6 also. Is that making sense? Are there any questions about this? So if you plug that into the formula, let me copy this formula again. If you plug this in, this gives you, well, all of these are the same, right? They are like the same numbers. So they're the same. So there are three of these. Okay. So it gives you three of the blue, of the red ones. So it's 3 times the probability of S1. There are also three of these minus 3, the probability of S1 intersection S2, because they're the same value for the probabilities, plus the probability of S1 intersection S2 intersection S3. So that's where you get 3 times the probability of S1. It gives you 3 times 1/3 minus the probability minus 3 times the probability of 1/6 plus the green one, which is 1/6. So what does that give you? It gives you 1 minus what? Minus 1/2 plus 1/6. Right, and this should be yes. Oh, okay, okay. So the moment of truth. Is that making sense? So it's 2/3, which is what we had found before. Is that okay? So just to like do one more, like for example, so what if you had 4 friends? Case of 4 friends. Well, then you would have to look at the probability of S1 union S2 union S3 union S4. And that, I mean, there's a similar formula, but this is the probability of S1 plus probability of S2 plus probability of S3 plus probability of S4. And then you have to look at all the possible intersections. So you could do probability of S1 with S2 minus probability of S1 with S3 minus a probability of S1 with S4. Okay. Minus the probability of S2 with S3 minus the probability of what? Let's see. S2 with S4 minus the probability of S3 with S4. And then you kind of have to do the same with the triples, but now it's plus, so it alternates. So the probability of S1 with S2 with S3 plus the probability of S1 with S2 with S4 plus the probability of let's see which am I we get 4 here, so S2 with S3 with S4. I think I don't have that one. Right. I think am I missing is 4. It should be like here, the one that's missing is 4, the one that's missing here is 3, the one that's missing here is 1. And there should be okay, plus the probability of S1 with here one's not present. Here, okay. So
I think Q should be missing on this one.
which one am I missing?
On the last one, I think it should be 1, 3, 4.
1, 3, 4. Perfect. Yeah, I'm looking at here. Right, because here 4 is missing. Then here 3 is missing. Here, I should have done the one where 2 is missing first. Right, like maybe to go in order. 1, 3, 4. Right. Because now 2 is missing there, and then I put like the one where 1 is missing. Okay. So I put 2, 3, 4 minus the probability of S1 intersection S2 intersection S3 intersection S4. Okay, so of course, like I would give you this formula. That's what I was saying. I'm not expecting you to know this, but like this is kind of like the, you know, this is like these are like the red ones. These are the blue ones. These were the green ones. And this is like the new one, because now you have 4 friends, but this gives you 4 times the probability of what? Now it would be the red one, what? Like now 1 over n, so 1/4 minus how many terms are there is 6. 6 is just because it's 4 chooses 2, if you want to know. So this is really 4 chooses 2. And how about the probability of the blue ones now? The probability of the blue ones would be n minus 2 factorial over n factorial. So I would, for n equals 2, that would be 2 factorial over 6 factorial, over 4 factorial. Plus the green one, which is the green one would be how many green ones do we have? We have 4 terms because it's 4 chooses 3. This is 4 chooses 3. And what's the probability of that one? That would be in the case of n equals 4, it would be 1 over 4 n factorial. So 1 over 4 factorial. And then the last one is 1 minus n factorial. Yes, if I'm not mistaken. Yeah, so it would be minus 1 over 4 factorial. And here, okay, of course, and here you can simplify it a little bit. It would be 1 minus 6, what's 6 over 2 factorial? I mean, like 12. What is 4 factorial? 4 factorial is 12, 24 plus 4 over 4 factorial is 1 over 3 factorial. So that's 1 over 6 minus 1 over 4 factorial. 4 factorial is 24. So it's 1/2, right? This is 1/2 plus 1/6 minus 1 over 24. And now I'm getting lazy and let's just leave it at that. But I mean, that is some number, right? I can put in Wolfram Alpha because like I don't want to do it on my own here. So 1/2, what is 1/2 plus 1/6 plus 1/6 minus 1 over 24. Okay, so that's 5/8. That's not too bad. Okay, and like again, I wouldn't. It's not that I'm expecting you to do the general case. Like the cool thing, just for those who are curious, is that you can kind of, if you work this like for the general case on n, hopefully you convince yourself, like, I mean, more like as a personal homework, because that this probability would be, if you do it for the case of general n, again, you just have to be careful with how you do it, but it's 1 minus 1 over 2 factorial plus 1 over 3 factorial plus minus 1 over 2 the n minus 1 over n factorial. Okay, which looks a lot nicer. And that, as n goes to infinity, goes in the limit as n approaches infinity, that converges to 1 minus 1 over e. So there you go. So that means when that, even in the infinite case limit, there's always like, that gives you like a probability, it's the probability stabilizes to 1 minus 1 over e, for what it's worth. So this is related to what's called like a Poisson process. Like, again, like I'm throwing like a bunch of words right now, but it's kind of like, my point was more kind of like that you see, like if you work it out with details in the case of n equals 3, you can kind of come up with a generalization for higher cases. Okay, I guess in practice, I wouldn't expect you to, like, at least something like the case n equals 4, I would expect you to know how to do, but this formula, since it's like for general and like, you know, I wouldn't expect you to, you know, do it if we just like, you know, like I wouldn't put this like an exam problem or something like that. But I think it's still, it is still nice to kind of see like that there's like a, you know, it's not complete, like the numbers are not completely random, like they kind of start converging to some fixed number and things like that. But it is a good, I mean, it is a good application. For case of n equals 4, like maybe you 4 factorial is 24. So maybe you didn't want to do like 24, like a list of 24 letters, right? So for n equals 4 is already like, you know, a faster way of getting the probability, you see? So it is not like a silly thing to do. That's, I guess, my point. Is that making sense? That's the power of generalizations, you know. But it's a cute application of that formula. Is that okay? But again, like for like the formula for this thing, for like for the union of 4 or like the union of 3, I would give you those formulas because I wouldn't expect you to remember them per se. Okay, so I did have, I don't know if I said it at the beginning of class, but today I did have to finish the class earlier. But so officially, this is where like the last topic of for the exam on Monday would, like on Friday we'll do new stuff. So today officially ends the material for the first exam. As I was saying, for those of you who came late, I'm finishing writing like a study guide with which formulas you need to know, which problems from the PDF you have to pay attention to. The exam will be very similar to those problems in the exam, some of the examples we have done in class. So if you have studied those, you'll be fine. And then I'll also, so I'll send you that tomorrow, and I'll send you tomorrow also like some practice exams for you to look at. But I mean, if you do like the practices, like the problems that I recommend and everything, you'll be fine. The first exam is like, you know, it's more like, I don't want to do anything too crazy because it's like, so if you have gone like over like the problems we have been doing in class, and like you should be fine. So, but yeah, I did need to stop earlier today, but I don't know if there are any last minute questions you wanted to ask me before we go. I mean, hopefully you find this entertaining. I think these are like interesting problems. It's a different flavor from the types of problems you have seen in other courses in mathematics, I imagine. On Friday, we'll get to like the actual one of the cards of probability, which is conditional probability. That's where like you can really start doing a lot of different things with the probability technique. So, but yeah, hopefully you're getting like a sense that it is like a useful thing. It's probably the most useful course that you could take in mathematics if you're not majoring in math. I think probability would be, like, you know, as much as I like geometry, I suppose probability is the most useful one, just because of all these relations to statistics and things like that. So, but yeah, if that's okay, so wait for just give me a couple of hours, and I'll send you the announcements with the recorded videos and a bunch of other information. But if not, I'll see you on Friday. If that sounds good.
Thank you,
I
Professor.
have a question.
Yeah, sure.
So I was wondering, I did some of the textbook questions,
Mhm.
and there was like some that I could not. I have the. I mean, I got the. It has the answer at the back, but I don't know how to like get that answer. So is it okay if I like email you to like
I mean,
ask?
you can always email me. I recommend if you're looking at the problems of the textbook. Do you have the 10th edition? Or
Yeah,
which
I think
edition
so.
do you?
Yeah, yeah.
Okay, so
10.
and that may also be the same with other editions. So maybe it doesn't matter if it's the 10th or not. But if you look at the textbook, it does like it kind of splits the problems into 3 parts, like the ones that are called problems, others that are called theoretical problems, and the other like the last
Right.
part called like self-test problems, like these ones.
Right.
These do have complete solutions at the back of the book, so I would just start there because I mean, even those self-test problems are already like 20 or something, like it's a good number of problems. So I would begin there. But yeah, if you have questions, I mean, I will try to answer them. But I would just start there. If I like on the PDF that I created, like of list of problems, I'm taking them from there just in case people want to, like I'm focusing more on the self-test problems just because those have complete solutions on the book. So I thought that would be more convenient.
Okay, got it.
Yeah, but yeah, you can email me, of course. Yeah.
Okay, thank you.
Okay. Yeah, sure, no problem.
Have a good day.
You too. You too. Okay. See you on Friday then.